Ever notice how our brains just love to put things in order?
Hmm.
Like say you walk into a library.
Yeah.
You wouldn't just see a big pile of books, right?
Right.
There'd be sections for different kinds of books.
Right.
Maybe even a whole system for where each book goes.
Yeah, like fiction and nonfiction and all that.
Exactly.
Mm-hmm.
Turns out math's kind of similar.
Okay.
Loves a good system.
Yeah.
And that's where this idea of categories comes in.
Okay.
But we're going even deeper today.
Right.
We're diving into the world of inexact categories.
So categories within categories.
Kind of.
Okay.
It gets pretty complex.
Yeah, I can imagine.
Luckily, we've got an expert to guide us through it.
Well, I'm happy to help break it down.
So, inexact categories.
Yeah.
It sounds kind of intimidating.
It's definitely not the easiest topic, but really it's just about looking at how mathematical things are related.
Okay, so instead of just saying these things are connected,
Yeah.
we're looking at the how of it all.
Exactly. It's like if you think about watching a dance performance.
I like where you're going with this.
Instead of just seeing a still photo of the dancers,
Right.
you're watching them move and flow together.
It's the difference between knowing something exists
Yeah.
and understanding how it works.
Exactly. We're not just talking about individual objects and connections anymore. It's more about looking at sequences of objects.
These sequences.
Yeah, like a chain reaction or a domino effect.
Okay, I'm intrigued.
And we want to understand the specific rules that make these sequences work.
So it's like a choreographed dance routine.
Exactly.
And each move leads to the next in a very specific way.
You got it.
Now, the research you sent over,
Right.
it mentions something called inexact sequences.
Right.
Does that connect to this domino idea?
Absolutely. An inexact sequence is like a very precise domino effect.
Okay, I can picture that.
But here's the thing.
What's that?
We're not just interested in that the dominoes fall.
Okay.
It's about how they fall.
So like the timing and the order they fall in.
Exactly. Every step of that chain reaction matters.
This is making me want to see some epic domino videos.
Huh?
But let's bring it back to the math.
Right.
In this scenario, what are our dominoes?
So in this case, our dominoes are mathematical objects.
Okay.
And the way they fall,
Uh-huh.
that's determined by functions called morphisms.
Morphisms. Those sound pretty complicated.
Think of them as the rules that govern how our mathematical objects interact.
So if the objects are the dominoes,
Yeah,
the morphisms are like the force that pushes them over.
that's a good way to think about it.
All right, so we've got our dominoes and our pushing force.
Right.
But what makes a sequence inexact?
So that n actually tells us something important about the sequence.
Okay, what's that?
It refers to the number of steps.
The number of steps. You mean like the number of dominoes lined up?
Exactly. An n-exact sequence has a starting point, an ending point,
Okay.
and n steps in between.
So if you had 5 dominoes lined up,
Right, let's say 5 dominoes.
that would be a 5 exact sequence.
Exactly. And to be super precise,
Okay.
mathematicians would say it has 7 terms total.
7 terms, why 7?
Because you have your 5 dominoes
Right.
plus the starting point and the ending point.
Ah, I see. It's like counting the spaces between the dominoes, not just the dominoes themselves.
Exactly. It might seem like a small detail,
Sure.
but that level of precision is really important in math.
It's all about being specific.
Precisely. It helps us describe these sequences in a clear and unambiguous way.
So we've got our dominoes,
Uh-huh.
we've got the n that tells us how many steps are in the sequence.
Right.
What else makes these sequences exact?
This is where it gets even more interesting.
Oh, I'm intrigued. Lay it on me.
N-exact sequences have these special types of morphisms that control how the dominoes fall.
So it's not just any random pushing force.
Not at all. We're talking about very specific types of morphisms called n-kernels and n-cokernels.
N-kernels and N-cokernels. Those sound pretty intense.
They might sound a bit intimidating,
Just a tad.
but they're actually quite elegant when you break them down.
All right, I'm ready. Break it down for me.
So let's start with n-kernel.
Okay, N-kernel. What's that all about?
Think of it like this.
Yeah.
The n-kernel is what needs to happen for a domino to topple the next one.
So it's like a set of conditions.
Exactly. It's like the domino is saying,
Okay.
hey, I'll only fall if you push me with this much force in this direction.
I like that.
It's all about the setup.
So the N-kernel is all about the before.
Yes,
The precise conditions needed to trigger the fall.
precisely.
What about the N-kernel?
Ah, good question.
Is that like the aftermath of the domino falling?
You've got it. The N kernel tells us what happens after a domino falls.
Okay.
It describes how the system changes as a result of that domino falling.
So they after to the n kernels before.
That's a great way to put it.
So we've got these n-exact sequences with specific rules about how the objects or dominoes interact with each other.
Yes.
And these n-kernels and n-co-kernels are kind of like the rules of the game.
They're like the rule book that makes sure everything happens in just the right way.
It's like a carefully choreographed chain reaction.
Exactly. And the amazing thing is, these n-exact sequences, they're not just some abstract mathematical game.
Okay, so there's more to it.
Oh, there's much more to it. They're actually incredibly powerful tools.
What kind of tools?
Tools that help mathematicians understand how different parts of math fit together.
This is what I love about math.
Yeah.
It might seem abstract at first.
Right.
But it always leads to these amazing insights.
It's about finding the hidden connections.
Before we get to why this matters so much.
Okay.
There's something else in the research I wanted to ask about.
Sure. What is that?
It keeps mentioning the maximal n-exact structure.
Ah, yes. The maximal n-exact structure.
What in the world does that mean?
Yeah, that's a great question. And it's really at the heart of what makes this area of math so fascinating.
And I'm guessing it's not something we can just Google, right?
Not quite.
All right, well, I'm all ears then.
I'm ready to explain. Imagine you're watching the most amazing domino effect.
Okay.
Not just a straight line, but something really complex, different sizes, maybe even different materials, and the dominoes are like flying through the air and everything.
Now I really want to see this domino setup you're describing.
It's all about finding the most incredible chain reaction imaginable.
And how does that tie into the maximal n-exact structure?
That's exactly what the maximal n-exact structure is.
Really?
It's like the blueprint for the most intricate, most interconnected domino setup possible.
So it's not just any chain reaction. Yeah. It's like the ultimate chain reaction for that system.
Precisely. It's about finding the most complete set of rules for how those dominoes can fall.
Okay, I think I'm starting to get it.
Like, remember our library analogy?
Yeah. Imagine instead of just organizing books by genre.
Right.
We had a system that considered everything.
Everything.
The author, the year it was published.
Okay.
Maybe even the color of the cover.
Wow, that would be a really detailed system.
The maximal n-exact structure is like finding that ultimate system for our mathematical objects.
That makes sense. It's about uncovering all the hidden connections within a system.
Exactly.
But how do you even begin to find something like that?
Well, that's where things get really interesting.
Okay, I'm ready. Tell me more.
Mathematicians have these special tools they use.
Okay.
And one of the most fascinating ones is something called a functor.
Functor. That sounds kind of like a made-up word.
It might sound a bit strange.
It does.
But it's a really powerful concept.
Okay, what do functors do?
Think of them as translators between different categories.
Translators?
Yeah. Like imagine you have one way of organizing books by genre.
Okay.
And another way of organizing them by color.
All right. I'm with you. A functor would be like a tool that lets you switch back and forth between those two systems.
So it's like having different lenses to view the same thing.
Exactly. Each lens shows you different connections and relationships.
That's a cool way to think about it. So functors help us see things from different perspectives.
Exactly. And here's the really important part.
What's that?
Functors don't just translate, they actually preserve the structure of the relationships.
What does that mean exactly?
It means that the connections between things stay consistent.
So if two books are related in the genre system, they'll still be related in some way in the color system.
Precisely. The functor makes sure those relationships aren't lost in translation.
That's pretty amazing. So we've got our categories.
Right.
Our n-exact categories with those domino-like sequences.
Yes.
And now we have functors, which are like these special translators that help us move between categories without losing any information.
You're getting it. It's like having a key that unlocks the hidden connections between different areas of math.
I like that analogy. A key to unlock the hidden connections.
So now to get a little deeper into the paper.
Okay.
The authors talk about specific operations called PBCN and POCN.
PBCN and POCN. Those sound pretty technical.
I know, they might look a little intimidating.
Yeah, just a bit.
But really, they're just specific ways of working with these functors.
So if functors are like keys,
yes,
these PBCN and POCN operations are like the hands that know how to use those keys.
Exactly. They're the tools that help mathematicians unlock the secrets of the maximal n-exact structure.
I see. So it's like having the right tools for the job.
Precisely. They provide a systematic way to explore these complex relationships between categories.
It's amazing that mathematicians have developed such powerful tools for understanding these things.
It really is. And what's even more amazing is that these ideas, they have applications beyond just pure math.
Really? Like what?
Well, think about something like network theory.
Network theory.
Like social network.
Oh, okay. I see what you mean.
Millions of people interacting online.
Trying to understand how information spreads.
Exactly. And that's where inexact categories can help us.
How so?
Imagine representing each person as an object.
Okay.
And their interactions as morphism.
So you're like creating a mathematical model of the network.
Exactly. And by understanding the maximal inexact structure,
right,
we could potentially identify the most influential pathways of information flow.
So you could see how ideas and trends spread through the network.
Precisely. It's like seeing the hidden structure behind something incredibly complex.
That's incredible. It's like finding the hidden architecture of the internet.
And it's not just social networks.
What else?
These ideas can be applied to data analysis.
Data analysis?
Yeah, like imagine trying to find patterns in huge data sets.
Okay.
And exact categories could help us unlock those hidden structures and make sense of the information.
So it's a powerful tool for understanding complex systems. This is blowing my mind. I never would have guessed that these abstract math concepts could have such real-world applications.
That's the beauty of mathematics. It has a way of revealing the hidden connections in the world around us.
This has been incredibly eye-opening. So we've talked about the what and the how of inexact categories, but what about the why? Why is this area of math so important? So we've gone deep into these systems and structures.
Yeah.
But what's the real impact of this maximal and exact structure?
Yeah.
Like in the real world?
That's the amazing thing about theoretical math.
What's that?
It can have these far-reaching applications you wouldn't expect.
Okay, give me an example.
Think about networks.
Like the internet.
Yeah, or even something like a social network.
Millions of people.
Exactly.
Countless interactions.
And trying to understand how it all works.
It's a lot to wrap your head around.
But using inexact categories, we can actually model those networks in a new way.
How so?
Well, imagine each person on the network is an object, and their interactions, those are our morphisms.
So you're basically creating a mathematical map of the network.
Precisely. And then the maximal inexact structure, that could reveal the most influential paths for information to flow.
So you could see how ideas and trends spread through the network.
Exactly. It's like finding the hidden structure behind something incredibly messy and complex.
That's wild.
And it's not just social networks.
What else?
This has implications for data analysis.
Data analysis, how so?
Imagine trying to find patterns in these huge data sets.
Right, like trying to find a needle in a haystack.
And exact categories. They give us new tools to uncover those hidden patterns.
So it's not just about organizing information.
No.
It's about understanding the underlying structure of the information itself.
Exactly.
It's like you're not just reading the book.
Yeah.
You're understanding how the author put the book together.
Precisely. And that deeper understanding, it can lead to all sorts of breakthroughs.
In any field.
Potentially. From medicine to finance to who knows what else.
This is incredible. I never would have imagined that something as seemingly abstract as inexact categories could have such a tangible impact.
That's the beauty of math.
What is it?
It has this way of uncovering the hidden connections in everything around us.
It's like you're seeing the world with a new set of eyes.
Exactly.
This has been an amazing deep dive. A huge thank you to you for breaking it all down for us.
It was my pleasure. It's always exciting to talk about this stuff.
And to our listeners, we hope you've enjoyed this exploration of inexact categories. Remember, even the most complex ideas can be broken down and understood. And who knows, those ideas might just change the way you see the world. Thanks for listening. Okay, so get this. We're diving into higher homological algebra.
Oh boy.
But seriously, it's going to be fascinating. We're talking about mathematical categories, but picture them like seriously complex Lego structures, all linked together.
That's a really good way to think about it. It's like we're trying to figure out the blueprints.
Exactly. And that's where this paper by Carlo Klapproth comes in. It's called On Inexact Categories I, The Existence and Uniqueness of Maximal and Exact Structures. And trust me, it's a wild ride.
Yeah, this paper is all about a special kind of structure inside these categories, ones that are n-exact. But to get what that even means, we got to lay some groundwork.
Right, let's do it. So just starting with the basics here. What are categories in the simplest terms?
Basically, they're collections of objects, but the really cool part is how they connect. Imagine, like, let's say our objects are numbers.
Okay, yeah, makes sense.
So we've got, say, 1, 2, and 3. But we're not just looking at them individually, we're looking at what happens when we add them together, like 1 + 2 = 3. Those actions are like the glue that holds these objects together. We call them morphisms, and they show us how everything's related.
So it's not just about the numbers themselves, but the actions, the morphisms that link them together.
You got it. And these actions have to follow specific rules, kind of like a game, and make sure everything inside the category works together in a logical way. And to really understand these categories, mathematicians use these things called finitely resolved functors.
All right, wait. Finitely resolved functors. That's a mouthful. Can you break that down for me a bit?
Sure. Think of functors like special lenses that let us zoom in on specific parts of our categories. They help us find patterns and connections we might not see otherwise. And finitely resolved just means these lenses are made to work with categories built with certain rules that have to do with these n-exact sequences we'll get to in a bit.
So we've got our categories, our objects, the morphisms connecting them, and now these functors that help us analyze them. But where do n-exact sequences fit into all of this?
Well, that's where things get really interesting. Imagine these n-exact sequences as special arrangements within our categories. They're like building blocks that make up bigger structures, and the n just tells us how long those structures are.
So using our Lego analogy, if the whole structure is like the category, the n-exact sequences are specific ways to put the Lego bricks together.
Exactly. And for a category to be considered n-exact, these sequences have to act in very specific ways, following a set of rules or axioms.
Like a set of instructions for how those sequences can be built within our category.
You got it. These axioms make sure everything fits together logically. They basically control how these sequences interact and overlap. It's like defining all the allowed ways to build with our Legos, but on a much more complex level. It's kind of like we've got these instructions for building with our Lego chains, making sure everything connects the right way.
So these axioms are what make sure our whole Lego structure is solid, even at this tiny chain level.
Precisely. And in this paper, Klapproth looks at what happens when we build bigger and more complex structures within these n-exact categories.
And that's where the idea of maximal structures comes into play.
Yeah. Okay, so think of it this way. We're building a Lego spaceship, right? And we've got all these n-exact sequences, these chains we've carefully put together. And we want to see just how big and complicated we can make this spaceship while still sticking to the rules of our n-exact category.
So, like, we're trying to build the coolest spaceship possible without breaking any of our Lego rules.
Yeah. And what Klapproth proves is that every n-exact category has a limit on how far you can build. There's one ultimate, most complex Lego spaceship we can create. That's the maximal n-exact structure.
So we're talking about finding the blueprint for the most intricate Lego creation imaginable, given a set of rules and a specific set of bricks.
Exactly. And this isn't just some mathematical what-if. This has some seriously big implications.
Okay, you've got me intrigued. Tell me why this maximal structure idea is such a big deal.
Well, it's like finding this organizational principle for mathematicians. Imagine trying to categorize every Lego creation ever. It'd be chaos, right? But if you know the rules, and you know there's a maximal structure for each set of rules, then you've got a framework for understanding even the most complicated creations.
So it's like having a key to unlock a deeper level of understanding within these categories. How does Klapproth even go about proving this maximal structure exists, though?
He uses some pretty advanced math tools. They're called PBCN and PORPhi. Basically, they're operations we can use on categories, ways to rearrange those n-exact sequences.
So like we're taking our Lego spaceship and putting it through a bunch of modifications, using PBCN and POCN as our tools.
Exactly. And by using these operations in a very particular way, Klapproth shows that we always end up with this one-of-a-kind maximal structure. It's like no matter how you twist, turn, or rebuild those Legos, following those rules will always lead you to the same, most complicated creation.
That's incredible. But I have to ask, how does this matter? Outside of, theoretical mathematics, are there any real-world applications for this? So it's like we've got this amazing blueprint, but what do we actually do with it?
That's the really cool part. This finding has repercussions in all kinds of areas of math, especially this thing called representation theory.
Okay, yeah, I think I've heard that. What is that again?
It's basically about finding different ways to look at the same Lego structure. Imagine you've got our spaceship, but we can represent it with like numbers or even music or a dance. Each representation shows us a different side of the structure, but they're all connected.
So like seeing the same thing from different angles.
Exactly. And here's the kicker. This whole maximal and exact structure thing gives us a whole new way to understand these representations. It's like this master key that unlocks connections between these totally different ways of looking at the same math object.
So not just organizing categories, but using that to like crack the code of representation theory too.
You got it. It's like the blueprint for our Lego spaceship doesn't just tell us how to build it. It also shows us hidden patterns in how we could represent that spaceship in music or dance even. It's kind of a deep connection when you think about it.
No, yeah, that's really wild. It's amazing how these super abstract math concepts can end up being so important in other areas.
It really is. It shows how everything in math is connected and how discoveries in one place can suddenly make things clearer in a totally different field.
Well, I'd say we've gone pretty deep today. We've covered the basics of categories and n-exact sequences. And then, of course, this mind-blowing concept of maximal structures. And we even touched on how it connects to representation theory. So before we wrap up, is there one last thought you can leave us with today?
Here's something to chew on. We've been looking at these maximal structures with those specific rules from our axioms, right? But what if we just tweak those rules a little?
Like messing with how our Legos connect.
Exactly. What if we change how long our n-exact sequences can be? Do these maximal structures change in a predictable way, or do we get completely new, even more complicated structures popping up? That's something mathematicians are still trying to figure out. And it shows that even in math, which seems so structured, there's always something new to discover.
It's like our Lego universe just exploded.
Yeah.
And there you have it, folks, another deep dive in the books. See you next time.
Ever catch yourself wondering how mathematicians sort through like all the stuff in the math universe? It's got to be like some crazy filing system, right?
Yeah.
For all those equations and numbers and things.
That's a pretty good way to think about it.
Well, today we're diving into a really interesting approach to this whole filing system idea with something called n-exact categories.
Sounds a bit intimidating, maybe?
Just a tad. I have to admit, when I saw this paper by Carlo Klapproth, the title alone, A Functorial Approach to N-Exact Categories, I kind of gulped.
Yeah, I can see that.
But you know what they say? That's why we do these deep dives, right? That unpack this stuff. So let's start simple. For anyone who's not a math whiz, what exactly are these n-exact categories?
Well, remember how you said like a filing system?
Yeah, for all the math objects.
Right, so imagine those, but with a really specific structure. Like there's rules about what goes where.
Okay.
And those rules about how those math objects connect to each other, that's basically what makes it n-exact. It's like subcategories within the system, you know?
So it's not just the objects themselves, it's the very specific way they're all like linked up.
Exactly. You got it.
Now I gotta ask, why should anyone care about this? Is this just mathematicians geeking out, which, hey, no judgment? Or does it have like broader implications?
Oh, it goes way beyond just geeking out, I promise.
Okay, good.
Think about how networks are structured.
Yeah.
Like even social networks or the internet.
Yeah.
These n-exact categories, they might help us understand, say, how information flows through those networks or find like the really critical points in them.
Whoa, so we're talking about like real world insights from this abstract math.
Exactly.
Okay, that's pretty cool. So let's get into what Klapproth is doing in his paper. He's got this functorial approach. I gotta be honest, that sounds kind of scary.
It does sound a bit technical, yeah.
Right.
But think of it this way. Instead of getting lost in each individual file, he's looking at the whole filing cabinet.
The big picture.
Right. How is the whole system organized? What's the underlying structure, the rules of the game?
And he's using this to like redefine, reclassify these n-exact categories.
Exactly. He's trying to find a more, I guess you could say, elegant way to understand them, a new perspective.
And this leads him to, he talks about maximal n-exact structures. Now, what makes a structure maximal? It sounds kind of like impressive.
It is impressive. Imagine you're organizing a library. You could do it by genre, right? Then author's last name, then publication date. A maximal structure is like finding the absolute most efficient, the most like comprehensive way to organize those books.
So every single book has its perfect spot based on everything about it.
Exactly. And that kind of clarity, it's incredibly powerful for mathematicians.
That's really neat. Now, Klaproth also gets into weak isomorphisms versus homotopic equivalences. Can you shed some light on those?
Sure. Imagine you have two different maps of, say, a city.
Okay, got it.
One is your classic street map. The other's like a subway map. Totally different.
Yeah, totally different.
But they both describe the same city. You can use either one to get around.
So even though they look different, they serve the same purpose.
Exactly. In this n-exact world, weak isomorphisms and homotopy equivalences, those are like our two maps. They're ways to compare and connect objects, and they might look different, but they basically tell us, are these things really different, or are they just different paths to the same endpoint?
So Klapproth is trying to figure out if these different looking connections are actually all that different.
You got it. He's looking for the essence of those connections.
Man, it's so cool how this abstract math stuff can be like a metaphor for real life.
Right.
And we're just scratching the surface here. What I find even more interesting is how he connects this work to other areas of math, like quasi and abelian categories.
Yes. And that's where it gets even more juicy, exactly.
So we're basically talking about like a family tree of math categories with execs and quasi-abelian as different branches.
I like that, a family tree.
And just like a real one, seeing how these branches connect, it can tell us a lot about each one and how the whole family like evolved. That's a really cool way to think about it. Now, you mentioned earlier that this research, it could have implications beyond just, the math world. What did you mean by that? Where could these insights actually be applied?
Oh, absolutely. Think about computer science, for example.
Okay, yeah.
Categories in general, they're already used a lot to model data types and how they relate. So understanding this inexactness, it could give programmers new tools, right, to organize that data better, manipulate it in ways we haven't even thought of.
So even if most programmers don't need to get deep into the weeds of this inexact stuff,
right,
the insights could lead to better software, faster algorithms, all that.
Exactly. It's about building a stronger foundation, theoretically, which then supports a ton of practical stuff.
That's wild. What about other fields? Could this apply to physics or engineering?
For sure. Theoretical physics especially. They rely on all sorts of crazy math structures to describe the universe. This work on categories, it might give them new ways to model really complex systems, like in quantum mechanics, even cosmology.
Okay, now that is mind-blowing. So from organizing data to the mysteries of the universe, categories are kind of a big deal.
They really are. That's what makes this research so exciting. It's about these fundamental structures that pop up everywhere in science and math, finding the hidden connections that tie everything together.
It's like what we were saying before about inexact categories being like secret passageways in a castle.
Right.
Those passages, they could lead to whole new rooms, whole new wings that we never even knew existed.
Exactly. And who knows what we'll find there? That's the beauty of math. Constant exploration, always something new.
And speaking of discovery, this functorial approach, it's really shifted how I see things, like putting on a new pair of glasses.
That's powerful, isn't it?
Totally. You zoom out, see the bigger picture, suddenly it's all connected and elegant. And honestly, I think that's a good lesson for anyone, even if they're not, a math person. Sometimes you got to step back from the details, look for the overall structure, the patterns.
Right.
It's like seeing the forest instead of just the trees, or, well, in this case, seeing how all the forests connect underground.
Exactly. And what Klapproth's doing with this functorial thing, it's like he's giving mathematicians new tools to map out those connections, like a whole new level of detail.
A stronger magnifying glass for some really, really intricate stuff.
That's a great way to put it. It's about getting to the core, those fundamental building blocks, and then seeing how they affect everything else.
So even if, the average person listening isn't going to need to know the ins and outs of inexact categories.
Right.
The point is this kind of thinking, it's powerful.
Oh, absolutely. Looking for those patterns, the connections, the structure underneath it all. And not just in math, in anything.
Yeah. It's like training your brain to see the world differently, appreciate how complex it is, but also how beautifully put together.
And who knows what other amazing stuff we'll find once we're looking at things that way.
That's a great question to leave everyone with. As we wrap up our deep dive here into this inexact world.
It's been fun.
It really has. And to everyone listening, remember this learning, it never stops. So keep those questions coming, keep exploring. Who knows? Maybe you'll find your own EBUN version of an inexact category in whatever you're into. Hey everyone, welcome back. Ready for another deep dive? We're going to try to unpack some pretty dense math today.
Hello.
We're tackling this paper on inexact categories I, the existence and uniqueness of maximal inexact structures. And honestly, even the title's a mouthful.
Yeah, it's definitely a mouthful.
So before we even get into it, what are we even talking about? What are n-exact categories?
Well, at their heart, and exact categories, they're really just a way of, categorizing, like putting things into their own little organized groups, mathematical objects, but with a very particular structure.
Okay, so like we're grouping mathematical objects, got it. But what kind of objects? Give us an example.
Think about like geometric shapes.
Hmm.
Triangles, squares. You could group those by the number of sides they've got, right? And exact categories, it's kind of similar, but instead of shapes, it's more abstract stuff. Think algebraic equations or even like geometric spaces, but way more complex.
Okay, so the n in n-exact got to be important. What's it about?
Right, so you've got exact categories, right? Those have been around for ages. They use these sequences of 3 terms, but in exact categories, they use way more. They use n plus 2 terms, and n. That could be any whole number.
Hold on, so instead of just 3 terms, we could have 4, 5, 100, even a million. What's the point of all those extra terms? Why is that so useful?
It's like, imagine you're looking at something under a microscope. The more powerful the microscope, the more detail you see, right? Inexact categories, they're like that super-powered microscope for math. They let us study structures that are way more, well, complex, stuff we couldn't even touch before.
I'm starting to see how this could be huge.
Oh, it is. It's especially helpful for understanding this thing called n-cluster tilting subcategories, which, without getting too in the weeds, are super important in this area of math called representation theory. It's basically about finding ways to visualize and understand really abstract algebra.
So we're taking something that's like super abstract and we're finding ways to actually picture it, to see its structure.
Exactly. And the cool thing is, n-exact categories, they've got this thing called being intrinsic.
Intrinsic. Okay, now you're just using big words. What's that mean?
It just means their properties, they don't depend on anything else. They stand on their own. Think of it like a puzzle piece, It's got its own shape, its own thing, whether it's in the box or part of the finished puzzle.
All right, that makes sense. So we've got these n-exact categories, our new tools for understanding complex stuff. What are we trying to do with this paper?
So this paper, it's all about finding ways to classify all the different ways we can structure these n-exact categories. Think of it like creating like a taxonomy for a new species, right?
Yeah.
You got to figure out its characteristics, how it all fits together.
Bringing order to the chaos. I like it. How do they go about doing that?
They use something called a functorial approach.
A functorial what now?
Basically, imagine you've got 2 maps, right? One's a regular map, shows you the streets and stuff. The other's like a topographical map, all about elevation. A functor, it's like a translator between those 2 maps.
So we're creating a way to move between different views of these categories, but making sure the underlying structure is still the same.
Yeah, exactly. And it actually builds on previous work by this mathematician, Enomoto. He used this approach for the simpler, exact categories. So this is taking it a step further.
So we're upping the ante here, taking it to the next level. This is getting exciting. Now, I gotta ask about this term. It keeps popping up. Maximal n-exact structures. What's a maximal about them?
Good question. So you can have multiple n-exact structures inside a category, right? Well, a maximal one, it's like the biggest, most all-encompassing structure. It's like if you've got all these different organizers for your tools, one for screwdrivers, one for wrenches, a maximal one would be like a giant toolbox that hold all those other organizers.
So it's like the ultimate container for all these structures.
Yeah, you got it. And what's really cool is this paper actually proves that for a certain type of category, there's always going to be one and only one unique maximal n-exact structure.
No matter what, there's always a biggest box to fit all the other boxes in. Amazing. Okay, let's take a pause here, but when we come back, let's dig into what all this means, why it even matters.
All right, we're back. And I'm still trying to wrap my head around these, like, structures within structures. It's a lot.
It's like we're going deeper and deeper into this mathematical rabbit hole.
And speaking of going deep, you mentioned this paper proves something pretty wild about categories with a certain property, right?
Right, we're talking about idempotent complete categories. It sounds complicated, but
It does.
it really just means that certain operations in these categories, they always have a clear, unambiguous result. It's like, following a recipe, you follow the steps, you always get the same cake, right?
Okay, so it's like a guarantee, a mathematical certainty.
Exactly. And what this paper shows is that for these idempotent complete categories, there's always going to be like a one-of-a-kind maximal n-exact structure. It's like a universal container for all the other structures inside that category. So it's like a missing piece of a puzzle, but once you find it, everything just clicks.
Precisely. But, we could talk about this theoretically all day, but where does it actually apply, right? Like, why should anyone care about these inexact categories?
Exactly. Bring it back down to earth for us.
Well, it's like finding a new tool, and suddenly you can build all sorts of things you couldn't before. Take representation theory, for example.
Which, reminder, is all about visualizing abstract algebra, right?
Exactly. Inexact categories, they give us this whole new way to look at these representations, especially the really, really complicated ones. It's like, imagine you're trying to study a cell, but you only have a regular microscope, and then, bam, someone hands you an electron microscope. Suddenly you can see all this incredible detail you could never see before.
So it's like upgrading from a magnifying glass to like a super-powered telescope.
Yeah, something like that. And this is huge, especially for fields that rely on representation theory, like even quantum physics.
Wait, hold on. Quantum physics, we're going there.
Oh yeah, it's all connected. So quantum physics often uses representations of certain groups, these mathematical structures that describe symmetries and transformations. And understanding those representations is key to understanding how particles behave at the quantum level.
Okay, so you're saying inexact categories, they might actually help us unlock some of those quantum mysteries.
They could, yeah. Now, I'm not saying they're the be-all and end-all, but they might offer a totally new framework for thinking about these things, a new way to approach the problem.
That's mind-blowing.
Okay.
But it's not just physics, right? Didn't you say something about computer science, too?
Oh, yeah, definitely. Computer science is all about structures, right? Data structures, algorithms. It's all about organizing and making sense of information.
So inexact categories, they're like a new way of thinking about how we organize and understand all that data.
Exactly. It's not about telling you how to code, but about giving you new tools to think about the underlying structure of information itself. Who knows what kind of breakthroughs we might find?
This is incredible. It's like inexact categories are this hidden language that connects all these different fields. But hold on, we can't forget about those other areas this paper mentions. What was it? Homological algebra and algebraic geometry?
Ah, yes, those two. Homological algebra, it's like trying to understand the shape of abstract mathematical structures.
Shape. But we're talking about equations and categories, not like physical objects, right?
Yeah, no, it sounds weird, but even though we can't see these mathematical objects, they still have a structure, a way they're put together, right? Homological algebra tries to capture that structure, that shape, by looking at certain properties. It's like, instead of just looking at a building, you're analyzing its blueprints, its framework.
So going deeper, looking at the skeleton, not just the skin.
Exactly. And exact categories, they give us new ways to do that, especially for structures that don't fit neatly into our old ways of thinking.
It's like we're adding new tools to our mathematical toolbox.
Okay, and what about algebraic geometry? Where does that fit in? Algebraic geometry is this amazing field where algebra and geometry, they come together. It's all about using the tools of algebra to study geometric shapes.
So instead of drawing shapes, we're describing them with equations.
Pretty much. And believe it or not, inexact categories could actually help us study certain types of geometric objects whose properties are like deeply linked to their inexact structure. It's like finding this secret passageway between the algebra and the geometry.
This is blowing my mind. So many connections, but we've covered so much ground already, and we've still got some really cool stuff to uncover in this paper.
Oh yeah, we're just getting started.
All right, back for one last push to unravel these inexact categories. We've seen how they could impact everything from the tiniest particles to the way we understand information itself. It's wild.
It really is. But we're not quite done yet. There's still some really intriguing stuff in this paper.
I believe it. Speaking of intriguing, there's a part here that had me scratching my head a bit, the section on weak isomorphisms and homotopy equivalences. Now, those sound like terms you'd need a math dictionary for.
Yeah, they can be a mouthful, that's for sure. But really, they're all about, comparing different mathematical structures, seeing how they relate to each other. Think of it like comparing two different blueprints for a house.
Okay, so even if they look different, they might actually represent the same underlying thing.
Exactly. So a weak isomorphism, it's like saying, hey, these two structures, they're basically the same, even if some minor details are off. Like those blueprints, they might use different symbols or layout, but they describe the same house at the end of the day.
So it's about seeing the forest for the trees, focusing on the big picture.
Yep, exactly. Now, homotopy equivalence, that's a bit trickier. Imagine like a map with two paths leading to the same destination. They might go in different directions, but they both get you there, right? It's kind of like that in math. Homotopy equivalence says two structures are connected, but maybe not in an obvious way.
Okay, so they're linked, but maybe by like a winding path, not a straight line.
You got it. And here's the kicker. What's really cool is this paper actually shows that for n-exact categories, these two things, weak isomorphisms and homotopy equivalences, they're actually the same thing.
Whoa, hold on. So two completely different ways of comparing these structures, they mean the same thing when we're talking about n-exact categories. That's pretty mind-blowing.
It is. It just goes to show, how elegant and interconnected all this math really is. And it has some pretty big implications for how we understand these categories, how they work on a deeper level.
That's incredible. But before we get lost in the weeds, let's bring it back to our listeners. We've covered a lot, but what's the takeaway for someone who might not be a mathematician? Why should they care about all this?
That's a great question. I think what we're really talking about here is the power of abstraction. Yeah, we're looking at n-exact categories, and it's high-level math, but the ideas behind it, they apply to so much more than just equations and theorems.
What do you mean? Give us an example.
Okay, well, think about it. The ability to see patterns, to organize information, to see the structure beneath the surface, those are valuable skills, right? No matter what you do. Designing a website, composing a piece of music, even just trying to solve a tough problem at work. It all requires that ability to think abstractly.
So in a way, these n-exact categories, they're like a super refined example of that kind of thinking.
Absolutely. Those people might not need to know the ins and outs of this specific type of math, but the way of thinking it represents, it's something we can all learn from.
I like that. So it's not just about the math itself, but the way of seeing the world, right?
Exactly.
It's like we've been on this incredible journey through the wilderness, marveling at each little detail, but now we're taking a step back, appreciating the whole view, the entire landscape.
Well said.
That's a great place to leave it. Big thanks to expert speaker for being our guide through this fascinating and, sometimes mind-bending world.
It was my pleasure. Always happy to talk about this stuff.
And to everyone listening, we hope this deep dive has sparked your curiosity, given you a new way of looking at things. Until next time, keep exploring, keep asking questions, and we'll see you in the next deep dive. Okay, I'll admit, n-exact categories sounds a bit intimidating, like something you'd need a math degree to even pronounce.
It does have a certain, shall we say, technical ring to it.
But what if I told you this is about hidden structures, like in information itself, how we categorize things, connect them, build understanding? That's what we're digging into. You found this fascinating paper on n-exact categories I by Carlo Klapproth. Dense stuff, but seriously cool.
Klapproth is on a quest, you see. He wants to understand these n-exact structures. Think of them like, organizational blueprints within categories of mathematical objects.
Right off the bat, though, we're hit with terms like idempotent, complete additive category. Got any plain English in you? What kind of math are we even talking, and why should anyone care?
You're not wrong. It sounds like we're speaking Martian. But at its heart, it's about relationships, how mathematical objects relate. Imagine, if you will, a family tree. Individuals, families, branches, the whole tree. Categories are like, they help us organize these mathematical objects, see how groups connect.
So additive just means we can do addition within those categories, like adding apples to apples.
Precisely. And idempotent complete. That just means things behave consistently. You perform an operation multiple times. The result stabilizes. Like flipping a light switch. On, off, the second on. Doesn't make it brighter.
Okay, I'm with you so far. But where do these n-exact structures fit into all this?
Well, that's where our friend Klapproth brings in another mathematician, a fellow by the name of Jasso. He's the one who actually coined the term, these n-exact categories. Jasso's work, you see, is all about formalizing patterns, the kind of patterns we find across different areas of mathematics, surprisingly.
Formalizing patterns, so like finding some underlying structure behind things that seem totally unrelated.
You've got it. It's finding the common threads, the hidden connections. N-exact categories, they're a new lens, a way to view and understand these connections. Like imagine musical scales, how they organize musical notes, and exact categories aim to do the same, but for mathematical objects and their relationships.
Now that's an intriguing thought. So how does Klapproth build upon this foundation laid by Jasso?
Well, Klapproth, he gets into some very specific technical distinctions. One example. He grapples with whether to use weak isomorphisms or homotopy equivalences when defining these n-exact categories.
Now, I have to admit that one stood out to me too. Weak isomorphisms versus homotopy equivalences. Sounds like a mouthful, but it seems pretty important to Klapproth to figure out which definition to use. Why is that?
It's all about using the right tool for the job. We're talking precision here. Both of those terms, they describe ways mathematical objects are essentially the same. But the context matters. Klapproth wants to make sure the definition he chooses, it's consistent, it's useful within the system he's building.
So, like choosing the right screwdriver, flathead versus Phillips. They both drive screws, but you need the right one for the job.
A perfect analogy. But to really grasp why this choice matters, we need to delve into how Klapproth uses these concepts to understand the very structure of n-exact categories. And for that, my friend, we need to talk about functor categories.
Now, functor categories, that sounds almost not fun. But seriously, what are they? And how do they play into these n-exact structures? Okay, so we've got like a basic understanding now of what n-exact categories are about and how they kind of connect to those broader mathematical ideas, right? But how do we really get a handle on these things? Klapproth talks about using something called functor categories. Can you break that down for us?
Absolutely. Think of functor categories like, say, a map. They reveal the relationships between different categories.
Okay, I'm visual. I like where this is going. Give me an example.
All right, picture a city map. It shows you the streets, the connections between them. Functor categories are similar. They show all those connections, but between different mathematical categories. You get this, they reveal how you can take an object from one category and transform it into an object in another category.
Okay, I'm with you. So if we're trying to understand these n-exact structures, functor categories are like the tool, the map we need to see how they're built.
You're getting it. Functor categories, they allow us to see how n-exact structures are embedded within these larger categories. Like a magnifying glass, we can zoom in on the specific relationships and properties that define those structures.
So to be clear, are functor categories just maps that help us visualize the connections and relationships, and then those n-exact structures are like the specific patterns within those categories that we can identify using these maps?
You've got it in a nutshell. Now, Klapproth, he doesn't stop there. He describes how these functor categories actually function. He brings up this idea of projective resolutions.
Projective resolutions. Now that sounds a little intimidating again.
I know. It sounds like something out of a sci-fi movie. But the basic idea is pretty straightforward. It's like taking a really complex mathematical object, something with all these moving parts, and breaking it down into simpler pieces that are easier to work with.
Breaking it down, huh? Like taking a whole pizza and cutting it into slices so you can actually eat it.
That's a great way to put it. We're talking about representing a complex mathematical object in terms of these simpler ones, called projective objects.
So these projective resolutions, they're like building blocks then. We use these simpler objects to try and understand the structure of those more complicated ones.
Exactly. And here's where Klapproth's work takes a really interesting turn. He's not interested in just any projective resolutions. He wants to look at the ones that specifically reflect the structure of, you guessed it, n-exact categories. This is where those weak isomorphisms and homotopy equivalences come back into play. Remember those?
Right. Those terms are starting to sound strangely familiar now.
It all connects. You see, Klapproth uses these specific kinds of projective resolutions to construct something he calls a maximal n-exact structure.
Maximal n-exact structure. Okay, break that down for me. What are we talking about now?
Think of it this way. It's like finding the ultimate blueprint, the master plan that governs the relationships between all the mathematical objects in a given category.
So we're talking about like a blueprint that explains how everything fits together in that category. But how do you even begin to find something like that?
That's the beauty of it. Klapproth uses those functor categories, those maps we talked about, to search for patterns within the projective resolutions of objects in the category. These patterns reveal the n-exact structure, the underlying organizational scheme, and the maximal structure. Well, that's the one that captures the most extensive, the most comprehensive set of relationships.
So it's almost like it's not just a plan, but the best plan for that category, showing how absolutely everything works together. But what does that actually mean in the grand scheme of things? Why is finding this maximal n-exact structure so important?
It gives us this incredibly powerful tool, you see. A tool for understanding how mathematical objects interact within a category. Imagine having a map, a perfect map that showed you every relationship, every single connection between buildings, streets, landmarks in a city. That's what a maximal n-exact structure does for a category. It gives us a complete picture, a deeper level of understanding.
So this maximal n-exact structure, it's like the master map for a category. It helps us see those hidden connections, right? But how does this translate into real applications? Where can we actually use this knowledge?
Now that's the million-dollar question, isn't it? We're still in the early stages of exploring the full potential of n-exact categories. But the exciting part is this. We could use them to understand complex systems in all kinds of fields, not just math. We could be talking biology, social networks, even something like the internet.
Wow. So this abstract mathematical concept could have some very real-world applications down the line. Speaking of abstract, you mentioned that Klapproth's paper talks about these maximal and exact structures being unique. That word seems really important here. Can you walk me through that?
It is, isn't it? It's like we're not just talking about some esoteric mathematical idea. We could be talking about mapping the human brain, predicting how information flows online. It's heady stuff.
We're glimpsing a whole new way of understanding the world.
Precisely. And to think it all goes back to these structures, these mathematical structures.
You said it, abstract structures. And speaking of that, you mentioned earlier that Klapproth's paper talks about these maximal and exact structures being unique, right? That word seems really important here.
You're picking up what Klapproth's putting down.
Yeah.
Unique, that's the key. What he's saying is, for any given category, there's only one maximal and exact structure that perfectly captures those relationships.
It's not like we can draw the map a bunch of different ways. There's just one true structure.
You got it. Like finding the Rosetta Stone, but for that category, we're not just describing what we see, we're uncovering the code, the hidden code that governs how everything works. It's powerful stuff.
Not just describing, we're decoding. No wonder this research got you so fired up.
I can't help it, it's exciting. This has the potential to change how we approach mathematics, and maybe even more than that. Who knows what we'll find?
It's been quite a journey. We started with n-exact categories, and I'll admit I was a bit lost at sea there for a minute. But now we're talking about unlocking fundamental patterns, maybe even the universe itself. So if our listener could walk away from this with just one big idea, what would you want it to be?
You know, for me, it comes back to that sense of wonder, that drive to look for those hidden connections. N-exact categories, sure, maybe they sound a bit abstract, okay, very abstract, but really it's about relationships, how information flows, how things connect, and that's bigger than just mathematics, isn't it?
It's finding those patterns that connect us all.
You said it.
This has been a mind-blowing deep dive. Thank you so much for guiding us through this. And to you listening out there, thank you for joining us. Until next time, keep exploring those big questions.